We are starting with regular talks, and I would like to make one announcement. This announcement is reflected in the program online, but it's not printed version. So after the coffee break, initially we planned to have two presentations, but we will have 3 presentations before the lunch, because during the conference, one of the participants came to us and said that he has a great idea to show us concerning what thesis we present, and this is actually, I think, quite relevant, because Sami Aref will present us our very efficient algorithm for exact solution of modularity, and at least for us practitioners, this is super exciting. So I'm really happy that he agreed to give this presentation, and this presentation will be third presentation after the coffee break and before the lunch break. But because we have hour and a half for the lunch, I hope we can accommodate for this. So this is a small announcement. So now let me introduce the first speaker, Łukasz Kraiński, and to advertise the talk that Łukasz will give a bit. Yesterday, Paweł presented us this framework for evaluating of different classical graph embeddings, and there was a question, okay, but is it any useful? Who would use it? So we thought that it would be nice to have some application of this framework, and today Łukasz will tell how he uses this framework in his work. So, okay. Łukasz, the floor is yours.
Yeah, thank you. Just a mic check. I think everything is working. Nice to be here. I'm Łukasz Kraiński from Warsaw School of Economics. So I'm a PhD candidate and research assistant. And so maybe I have the first talk today. I looked on the agenda, so it looked more like compared to, at least to the previous days, like a practitioner's corner. So I will start with this approach for sure. So let's see what I have. So scalable embedding-based graph generator. So the scalable, let's keep it for the last. And maybe you can also judge it if the word is in the right place. But let's start with agenda, which is quite brief. So just an introduction to the topic. So it will be mostly about random graphs. So I guess we have some experts here and everyone knows that, but I will divide them into, let's say, 3 groups. And then comes the embedding-based graph generator, which turns nicely into the EGG abbreviation. So I will talk mostly about that. And I have some initial evaluations with a benchmark, with a baselines, and a few real-world graphs. So that's the agenda. So I think no one in this room needs to be convinced that random graphs are useful, especially in the practical applications. I mean, algorithm design and analysis probably it's a part of the theory, and we had some nice talks about different algorithms, and we can analyze the average case scenario with that. We can do a sensitivity analysis if we have a new algorithm and we want to see if this is susceptible to some small perturbations in the network. But also there's much more. So actually, like optimization of operation research is quite close to what we do in our department. It's even in the name. So we even have to do that. So like calculating minimum spanning trees. Or some network flows in a transportation network with random graphs, it's all easier, and we can make it work and in practice. So social network analysis, we had I think this is all the rage right now. More and more social data, Twitter, Facebook, probably like maybe they will not beat karate in being 101 models or graphs, but there's a hot topic, and we had fake news, already. So that's a social network. I think there's also a model of influence coming today, or tomorrow. So it's quite valuable. And yeah, actually the next one is quite, I would say they are quite related, but probably after pandemic we should also make a specific case for epidemic modeling. So we also had a plenary talk, especially for that. So it's the randomized graphs. Even if we are running some practical applications, then this is all helpful. And yeah, we also even in our department we have some experience with random graphs in machine learning and data mining. So probably the companies are yeah, they want to use this data and use it for something like link prediction and more. And yeah, also there's a classical literature drug discovery. It's not our topic, but it's often mentioned that we have the constraints for proteins. So I think you are convinced that random graphs, there is a need for more random graphs. So yeah, I will divide the random graph models into three groups. So let's call the first one traditional models. So more or less they are, they have their age, they are well grounded, they are analyzed, their properties. And I guess everyone knows them. The names were already here for a few times. So we had a binomial model, preferential attachment, we have small word network, and yeah, two siblings, yeah, Chunglu and configuration. So actually the Chunglu model will be quite close. It's quite close to my heart because it will modify it in a second. So yeah, that's the first group. They are nice, but they have they are parametric. We can call that they are parametric. It's quite hard to tune them, let's say, to real world networks. So maybe we can have random graphs with explicitly built communities. So I think especially in social science, we basically always have graphs with communities. We had a talk yesterday about stochastic block model. So everything is coming together. Yeah, so probably variations of stochastic block model are the like traditional models with communities. We also have newer benchmarks, LFR, and already mentioned a few times, and with different variations, ABCD. So they all focus on communities. They are a little more complicated, but still they probably can't like model every real world network. So right now the research is focusing on the deep approach. Probably anything is susceptible to to this, yes, to neural networks and different architectures. So we can see it's already going on. We have some variational autoencoders. We have generative adversarial networks, also autoregressive models. This is recurrent neural network. Also, there was a reinforcement learning generator from 19, but yeah, you can basically already pick what you want, and they can generate like multiple graph distributions, because if we are talking about Chunglu, we have degree sequence, yes, but with those models, it's usually the case that it's more like a black box. The promise is that you just give a graph and you get something similar out, and probably people like practitioners like it for sure. Mathematicians probably hate it because it's a black box. So yeah, I think that's a problem and blessing and a curse. Yes, so we don't actually know, or we don't exactly know what is modeled. So that's a little problem, and also they are computationally intensive. So they are really computationally intensive. So for example, this graph VA is like tens of nodes. If you go to hundreds, it's already off the charts. So graph RNN, it's from Stanford University, the quite innovative model. It's expanded the limits, let's say, to 100 to thousands of nodes, but still it's you need a big machine and a lot of time to get sample out of that. Okay, so let's go to what we want to propose. So yeah, let's maybe omit the scalable part. You'll judge by yourself. But basically, we have some proposition for a model that models both directed, undirected, weighted, unweighted graphs. if there comes a question, I will already answer. There is no support for node or labels or edge labels, but we have weights, so maybe that's some compensation for edge features. And also this builds on the classical embedding, so I think it was mentioned that we distinguish between classical ones and the structural ones. So this one is on the classical embeddings. So yeah, basically we have a graph, or maybe an input graph. We need some embedding into a vector space. This can be like an arbitrary embedding. And also we need a partition of vertices into M communities. Basically, with those three pieces, the task is to learn some distribution over the graph. I know this is quite vague, but basically that's also what is used in those deep let's say models. So basically, we will model edge probability, every edge probability, and we want to sample from this easily sample from this probability distribution. So our assumptions are, so if you are wondering why we need embedding and why we need partitioning, it's more than just a graph. Yeah, so that's additional work. So we want to model nodes so that they are close to each other based on the distance in an embedding space, because we assume that embedding captures some properties, maybe not only, it can be anything, I guess. Like different embeddings may capture different things, but we always measure the distance between them, and we want to keep the nodes close in the new graph. And also, we want to control this mechanism of how much the distance affects the probability of an edge creation with some parameter, which will come up in a formula in a second. But basically, this partition C comes into play. So we need to optimize into something, like into some objective. So our pick is that basically this graph is mostly focused on the graphs with communities. So we want to retain the expected proportion of edges within and between communities. So that's why we need partitioning on the input graph, and that's what we can calculate inside the model. Yeah, so I will swap between implementation procedures and some model definitions. Sorry for that, but I thought that it would just make sense more to put it like that. So the first thing, yeah, we need to produce a possibly good embedding and good partitioning of the input graph if we don't have a ground truth, because sometimes we have. Then we are fitting geometric Chunglu model. So that's a modification of the Chunglu model, and then we sample. So yeah, 3 steps, and we are done. Yes. Yeah, that's a limitation. Yeah, it's a single graph. So from single graph, we want to have a distribution. So we assume that, yeah, there is a family of input graphs, and this is because we are using embedding. This is like a hard constraint on embedding-based approach that we need to limit to the single graph. So graph RNN, or the variational autoencoder, they generalize to set of graphs, input graphs, and yeah, that's right. But also the case, I will just finish. So the case is usually we have one graph sometimes. Yeah, I don't want to say in majority of cases, but it's a often case. So.
When you model a graph, there's a process you observe multiple instances of graph, so that you can go to the graph distribution with that single graph.
It's a limitation. Yeah, for sure. Yes.
Let me, because Łukasz already said what I wanted to say, but let me rephrase it. So what you have in practice? In practice, you have one graph, and you say, now I want sensitivity analysis of this graph. I don't have many graphs. There is one Facebook, there is one Twitter. But I say, okay, I want to be in a parallel universe where I can generate 1,000 graphs that are like Twitter, so that I can, for example, test the stability of my algorithm not on a single graph, but on multiple graphs that are very similar, but not exactly the same. And in such scenarios, you have one input graph on which you can...
Yeah, but yeah, in the case we want to multiply them, clone them, but not exactly one-to-one. And also that's a problem later. What is
You
that?
could change it to,
very complicated parameter of the model.
but you could change it to allow multiple input graphs, but we don't do it currently. But
Yep.
it's a good idea to expand.
At least you have to do some strong modeling assumption on how this graph was generated. Otherwise, if you choose a single instance,
Yeah, actually, yeah.
hard to, like,
Yeah, so we took a, let's say, easy way. So we kind of seeded to embedding. We say that embedding captures something meaningful, and basically it's like, if there's a research in embeddings, let's say area, then it will get better. Yeah, also. So we just hope. Yeah, we have some assumptions, but it's basically the embedding is like a big part of it. So yeah, we have some assumptions. I already said we are focusing on communities. Yes. So let me show you the formula, and then I hope that it will be clear. But still, yeah, before the formula. Okay, so how can we get a good embedding, and how we can get communities? I guess also everyone here knows that it was already mentioned multiple times. At least the community. So for the embedding, there are Pavel, you said like 400, 100, hundreds of algorithms to pick from. Like Node2Vec, DeepWalk, they are considered quite good from, let's say, empirically. But also we have divergence scores proposed. So it was the talk yesterday. So we have some tool to pick the better one or the best one. So that's a way to choose. And also when it comes to partitioning, ideally we will have ground truth. Sometimes it's the case. I will have some real network, so we have ground truth. Otherwise, we have Leiden, we have ECG, we have Louvain, we have all the new algorithms. So also we have some means to assess them. Yeah. So it was the part of other talks. So let's assume we have some embedding, we have some partitioning. They don't have to be good. I will also show what's the impact in the evaluation. So yeah, we start with geometric Chung-Lu. So let's assume we have a degree distribution, a degree sequence. So we start in a familiar ground, and then we change it a little. So we add this part where embedding comes in. So basically, our Chung-Lu model depends on the degree sequence, embedding, and some parameter alpha. This parameter alpha controls how much we, let's say, penalize edges for being for nodes that are distant. So we want to tune that, and basically, if alpha is 0, we come to Chung-Lu model. Yeah. So it's a generalization, but also we add this part, and this J is distance between the vertices in embedding space. So for every vertex, we have some embedding. It can be 32 dimensions. It can be 64. Of course, we can take the distance. And I didn't write what is a min and max. We just normalized the distances because for different embeddings we can get different distances. So we want to normalize it, and we also put some constraint on that. So yeah, we want to have that expected degree of vertex I is equal to the sum of probabilities. So from our model. So we want to tune that those weights x to match this condition, and also we have this additional alpha parameter, which is just an arbitrary exponent. But let's tune that in the next slide. Okay, so there are some proofs already on that model. So we can the model has a unique solution when the sum of degrees is higher than 2 times the maximum. So if you have a star graph, then you have a problem with that model. But probably this is I would say this is a mild condition. You don't want to probably model a star graph. It's in practice. So it's quite. So unique solution is that the solution is that finding those. I did it, yeah. Okay, that's the tradition. Yeah.
It's a unique
Yeah, so that we can find some weights x that we meet this condition that we are getting an expected degree for every vertex, because we don't know the x. We don't know this is this is not known because of this additional complication in the parentheses. So it's well defined, but there's no analytical solution, or at least we don't know about one. But actually, the weights can be approximated numerically, and this is like a gradient-based root search. So it's quite efficient in the sense we are not really we are converging quite quickly. Yes.
So it might be said that this uniqueness means that using this gradient search actually will lead us to global optimum, because any optimum is a global optimum because there is only one. Essentially what the theorem says.
Yes, that's right. So basically we don't have a problem with local global minimal. We have one global, and yeah, we don't need to use like a simulated annealing. Yes, so we have just those two parameters, like it's called learning rate, epsilon and delta, that is a desired precision. So we are just iterating until the condition is met. So we have a good enough weights. So yeah, with hat, I am just a notation. I'm showing what is coming from the model, and everything else is from the input graph. Maybe one note, just coming back. So this is for the undirected version, but if you put degree out, degree in, it's naturally it's simple modification. For weighted graphs, it's even simpler because degree it just changed. W hat, or sorry, this one, yeah, previous. Yes, this is a degree of expected degree, which we approximate, because
the Twitter is your input graph.
Yeah.
So you have a G is the input graph, and yes, you want to have a model which expected degree matches input graph.
Yeah, but just to add on it, so the idea is, okay, I see in the input graph actual degree, but if I sample some graph that I want to be similar, I say, okay, I allow the actual sample degree to deviate a bit, because I don't want to be too exactly matching the original graph, because then I would not have enough deviation for sensitivity analysis, for example.
Yes. So this is from the input graph, and also we have the hat from the approximation, because we are approximating. So everything with hat is from this process. Yeah, so let's say we find those weights. We have our condition is met. So we have this expected degree in every vertex. But as I said, we also want to have control over how much we penalize the distance. Yes, because the higher the distance in embedding space, the lower probability we want intuitively. So we need to control that somehow. So that's why this alpha exponent is optimized. I think Pavel have shown some similar formula with maybe different marking, but you can see that that's here where the partitioning comes in. So this again, the part without a hat is coming from the input graph. We can calculate the expected proportions of edges between and within communities, and if we don't know, then we have we need to find them, but then we don't know if they are the right ones. But yeah, so it's better if we have ground truth, but we also yes.
So again, just as it was discussed yesterday, of course we want ground truth, but if we don't have it, essentially this says that dense parts in original graph should be dense in the generated graph, and that's why we don't really need exact ground truth. Rather, we need something that tells us which parts of the graph should be dense.
And also
so even if we recover it with like Leiden, it's okay, because it doesn't have to be exactly ground truth.
And we also account for the density between the communities. So actually this, in our framework, this part is weighted. So this is just an average, but if we care more about the connections between communities, we can change the weight. Yeah. So I think default is just average. Yeah. So both intra and inter-community connections are more equally important. So we optimize the alpha. It's just more iterations, yeah, for the numerical approximation. So it's also approximation of alpha. So we approximate a lot, but let's see, we will have a result shortly. So the first step is sampling. So yeah, basically we have, as I said, we end up with the probabilities for each edge in a graph given the number of vertices. So the default approach would be just to sample from that, like every edge independently, and we should arrive in the expected number of edges. But we can imagine a, let's say, conditional sampling, that if we want to make sure we have one giant component, or we want to exactly have the fixed number of nodes of the input graph, because we can by accident just not sample enough nodes, we can impose some additional conditions. But right now it's yeah. I think we have probabilities for edge, so anything we want to do with that is on the plate, let's say.
Probability of graph being small, right? It's still accommodated.
So for probability of
True model, I guess that's the same for the symmetric true model. The probability of the graph is connected, the extension is small. So origination.
Yeah, so like of whole graph. I mean, that is the question, yes?
But that's what you're writing in your first bullet, right?
Yeah. So
that's
especially if you have many low degree nodes, you are likely to be disconnected. And what Łukasz, I understand, wants to say is that we can like
it's a condition.
Correct for it if we want a connected graph. Of course, maybe, for example, the simplest process would be rewiring, which kind of a bit,
break the model.
Break the model, but in practice, it's not such a problem, because usually the fraction of those problematic nodes is relatively low, so the general view of the graph will be similar.
But you lose the distribution.
Yeah. That's.
That was my question. So I think it's maybe confusing.
Yeah. So that's
conditioning.
That's a conditioning, but actually we are losing something. But again, I think in practice, this is sometimes this is if we are able, like if we are willing to lose this, then that's fine. And I think in the connected, if we have multiple components, then usually we just need to connect few graphs. Okay.
So you could do rejection sampling, but it would be super slow. So that's why.
Yeah.
So it's probably better to do rewiring and break the distribution a bit.
Probably I shouldn't put that last sentence, but it's actually we have the first part implemented, so it's only from the distribution we get. So yeah.
How do you hit the model maximum life?
So actually we just optimize to this condition, yeah, and then we optimize the weights of geometric Chung glue, and then we get the probabilities from the formula here. So it's just a gradient descent approximation. We don't use this.
You first do it for X alpha, and then later you optimize over
Yes. That's right. Yeah. So as I said, yeah, we do this for fixed alpha, then we tune the weights, then we pick the next alpha, tune the weights, but also alpha is this is.
But then you maximize the probability of observing the edges that actually exist in the graph.
Yes. So I mean the edges, they influence the probabilities because of the embedding, so it's a proxy. And then we just rely on what embedding detected, yes, the distance. So.
But in expectation, you get the degrees in expectation are the same as degrees in the original graph.
Yeah, that's the constraint. Yeah.
This is for fixed alpha, and for For
Yes,
any alpha, the theorem says you can find such parameters that give you this. And then in the second step, Łukasz says, okay, but I also want community structure to be preserved, and this is enforced by optimization of alpha, like on a higher level.
Yeah.
So you enforce these constraints on degrees, and it's by enforcing the constraint you get the parameters.
Yeah.
Yeah.
But you'll never be able to be perfect, I guess, with communities. Well, with degrees is always good, right?
Yeah.
But with communities, you just want to be as close.
Yeah.
Densities should be as close as possible to the original densities. And you just maximize, try to be as good as possible by tuning alpha.
Okay, so I guess I need to make it fast, but you know.
Started a bit late, so that's why I don't stop.
But still, it's just a table with results, so the least interesting part, I guess. And the experiment setup, yeah, first. So I think we'll manage in a few minutes. So yeah, I guess there's no surprise that the model was implemented in Julia language. And yeah, there was a small benchmark run with 4 real-world graphs, undirected, unweighted, just to make it simple. So yeah, karate need to be here, yeah, I guess. So yeah, just increasing number of nodes, just to also see how it scales, and different number of communities. I will also mention in every graph what we do. So yeah, we have some, let's say, traditional baselines. So we have Erdős and Barabasi graphs models. Also have stochastic block model to accommodate for communities, and yeah, one of the deep models to compare, and our egg model. So for every graph, the 42 dimensions node to vec was done. So based on our experience, it's good enough. And okay, so we have. Okay, let's go to the table already. I will just go through the first one. So the proposition in literature for degrees, like for distributions, to compare some divergence scores. So you was comparing maximum mean discrepancy. So that's also what we are calculating. So basically the degree and clustering, this is a divergence between distributions from the input and then sample graphs. And triangles and assortativity is mean and standard deviation for 100 samples. So basically for every graph there are 100 samples, and then a mean and a standard deviation is calculated. Runtime is just a mean. So for karate we have graph RNN is quite good. But if you look on the runtime, it's I think it's more than 2 hours just for 34 nodes. Okay, I run it on my MacBook, but probably if you use something better, it's good. But yeah, the deep approach wins, except for assortativity for Barabasi Albert. Then it gets interesting, maybe for me at least, that for 1,000 nodes, the deep model didn't converge in 24 hours. So that was enough for heating of my laptop. So we are left with the 4 other ones, and you can see that our approach is quite good. So clustering coefficient is hard to tune, as you see, but the degree is quite nice. Runtimes is still good. Okay, this was an email. Okay, in this graph, I think this is something worth noting, that, okay, of course, this is 13,000 nodes, so deep model is still off. But we used two embeddings. The two-dimensional embedding is an actual latitude and longitude from the network, because this grid EU is a electrical grid in Spain. So we have a true embedding, let's say. But it turns out that actually using the synthetic or embedding, or let's call it like that, it's better. So it's not only the distance in the, like on the globe, but actually this 32-dimensional is capturing something else. So yeah, still, yeah, I think we are good with all the statistics. Just runtime is better for Barabasi Albert. And the last one, the biggest one, is the GitHub. I think, yeah, it's also already shown yesterday. So here also the embedding-based graph generator is the best, but you can see it's actually quite hard for all the models to feed this bigger graph. So probably with the the higher the number of nodes, it's just harder to sample, to make a good distribution out of that. But actually, yeah, I think you can see that the triangles get quite close and assortativity is quite good. But yeah, still the runtime, it's yeah, it's few hours, 4 or 5 hours just to run 37 nodes. So yeah, that's the question about scalability. So that's the last slide. Yeah, so the algorithm is fast due to implementation. It's fast because we have efficient approximation, but it's still n squared. Yeah, so we can't beat that even yeah, with even faster implementation. So actually also there is an algorithm that Paweł mentioned, something approximation again. So we'll approximate and approximate until we make it faster. So landmarks. Yeah, so basically the concept is to group nodes into one node. And then we just make the number of nodes smaller, and then we calculate geometric Chung-Lu on top of that. But there's one problem or two problems with that. So yeah, so yeah, the good thing is complexity is n log n, but actually we have increased variability because if we collapse the landmark, we calculate the weights just one sentence. Okay, we calculate the weights for the whole landmark. But then we need to expand it to the real graph, to the input graph, and then we have bigger variability, and it can hurt the results. I just want to finish with the statement that in this problem, actually, it may be a good thing, because if you have the identity, if you have the same graph on the output, it's useless. If you have two different graphs, it's also useless. So there's a good question is which graph is good. So maybe it will be good, and this is for further work. Yeah, and then there are some references. So thank you, and yeah, sorry for taking a little more time.